Okay. Anyone taking the quiz yet? How was that? Second one's probably going to be a little more difficult. Probably going to be more fill in the blank, more kind of. And then someone asked about a study guide. The quizzes are probably going to be a fairly good study guide. And then just to be able to apply some basic discussion questions like what happens if we increase bulk density? What happens to infiltration if we increase bulk density? Infiltration goes down, right? So simple questions like that. If infiltration goes down, what happens to the water? I don't know how you write that, but if you can. Right, like, so just some very simple questions. Like, we're not getting into the whole difficult, big, long answer, super intricate thought process. Now, maybe by the end of the semester we will. We'll start to apply some of this stuff and have to think a little bit about it. Like, it's not going to be multiple choice fill in the blank. Listing, there will be a little bit of discussion to kind of make you think about the concepts that we've been talking about. So we moved on to soil erosion. I've moved away from Rick's PowerPoint and started doing my own thing. Because I spent more time fixing his stuff than I did having my own stuff. So if I've already got it made, why not use it? So over the last couple of week or so, I've talked about land degradation and soil erosion. Let me stop right here. How many of y'all have been watching the videos on YouTube? Is that an effective method? You like that? You click on that link to go straight to the playlist. Anybody else been watching the videos? That's good. All right. So land degradation, we know it's happening. It's our responsibility to slow it down because we know we can't stop it. So we're trying to conserve some of that soil erosion. We've talked about geological and accelerated. This was going to be part of the last exam. I just added it on here to go over it again, and I can get this in the video. We talked about some of the on-site damages, or off-site damage. We have 1.5 billion megagrams deposited, and this is like $45 billion worth of cleanup that we have to do over this thing that, like, we really can't stop. We need paper that just got printed. Like, we need these things. Hey, Cassie. We need that land so that we can grow crops. And so when we do that, we're influencing the environment, the natural environment of our system, and then also that each one of these things that we do, each one of these practices that we have, it has an equal and opposite reaction. So we can't just cut down the trees and go, well, that's cool. Something's going to happen for that. So there are people who calculate what's going, like if you go work for Weyerhaeuser, there are people who calculate what's going to happen when they cut down 60 acres worth of trees. From the time you cut it, they can look back at the rainfall, they can tell how much water erosion, the soil type, all of that stuff, and they can go, you know what? Maybe we need a strip cut rather than clear cut. Sorry, but I think that's going to have a detrimental impact way down the stream. Not necessarily right in the local community, the ecosystem right there in the forest. It will, but it's going to compound as it continues on down and out of the watershed and into another watershed. And so the impacts of the one thing that we do way up here can have a huge impact on something that we don't even know about. It's not even on our radar. So there are people out there who are taking this into consideration and not wanting to spend this $45 billion. And that's money. Where are we going to get it from? We're already playing with monopoly money as it is, aren't we? Okay. So, whole new different story. Anyhow, I think we kind of left off where I was talking about the mechanisms of water erosion. So we had this raindrop that hits the soil, kind of like a meteor or a bullet, and some detachment happens. Some impact and the soil shatters. Some of that soil is then transported down the slope and then deposited at the lowest point in the watershed, or it gets carried to the water, right? Because that's where everything's going anyhow, to a river. So it's picking up more soil as it continues on to the river, gets deposited, the river that's already flowing, already picking up soil on its stream banks, and we're just adding to that. So we're increasing the turbidity, and we're increasing the soil that we're losing. Now it's leaving our watershed and entering into another watershed, causing them problems. So we lose, and then they have to deal with the consequences of it. I think in the last slide I used that it was like 30 kilometers per hour, which is really about like 18 miles an hour. It's really hard for me to believe that a little bitty raindrop is traveling 20 miles an hour towards the Earth's surface. Again, there was someone that calculated that, and I have to trust them because I'm not going to sit down and calculate it, right? I trust them. We went over the types of erosion: sheet, which is a uniform removal across the whole system; rill; and then gully. We're not necessarily fixing this by any tillage practice, are we? You can't, like, that's a complete removal. Like shaving the earth's surface of this soil. It doesn't, you can't cover that up. Rill we can, and we have to, because our tractors would be bouncing all over the place. So we send one tractor out there and have them do the tillage over that, so we can kind of at least get some sort of flat land that's drivable. But what happens when we till? What are we influencing when we till? The soil, pore space, and what else? There's something like, remember we talked about there are different, the soil, that's the hot, that's the horizons, the structure. The soil structure is what's getting ruined, or altered, or changed. That's changing our pore space, which is changing our infiltration rate, which is sending the water where? Out. So we have to be careful how much we're tilling, because we're messing up the soil structure and the soil aggregate stability. But we have to, because we have this rill erosion that will eventually turn into gully erosion. And once it's gullied, it's gone. You can't do anything about it. Now your land is disjointed, and how are we going to get this tractor across that ditch, across this big gully? Now you got to build a bridge, or you have to stop, take the tractor to the other end, drive all the way down, and drive all the way back and around just to get over something this wide. So, something to be aware of. Some better pictures of the sheet erosion. Our rill erosion. And probably the best answer for this is to put some sort of cover on top of that. You aren't tilling a bowl. So for this, I would suggest planting some sort of cover. You'd probably have to put some straw mulch down, because it's not going to grow there. Like, so those are the types of things that at the end of the class I'm going to go, what's up here? What would you do? Well, we would till it. What does that impact? Soil structure, compaction, bulk density, like all of these things that I've been talking about over the class. I'm building up to that at the end. We'll talk about conservation tillage and strip cropping, cover crops, and how we can influence that. So, not driving the tractor across that. And so remember that we're losing 4 billion megagrams of soil per year. And so how do you calculate that? How do you quantify how much a soil is going to erode? So they came up with the universal soil loss equation. Heard of it before? Some people, not a lot of people. It's okay. It's a very basic, fill in the number. It's not something that you have to perform a lot of difficult calculations with. It's go find the value, insert it into parentheses, do the multiplication, get the number. All right? So we're going to go over those, I guess, over the course of the next couple of weeks for Module 2. And kind of what the implications are and how we came up with these and how we can use that to determine what our soil loss is going to be. Do we need to implement some sort of extreme contour strip tillage on slopes and terraces, or can we maybe just get away with planting cover crop and like be stable for a bit? Mainly for sheet and reel, it is not to a specific year, and it cannot predict the delivery to the streams. Then, because this one just wasn't good enough for people, someone really wanted to quantify it even more. They came up with the revised universal soil loss equation. And there's the modified, revised universal soil loss equation. And then there's the Peyton Rogers modified, revised universal soil loss equation. He spent his whole career trying to make this thing even more intricate than it already is, right? Because you know, people don't like simple. We like to make things super complicated. Let's add some extra factors in there. Let's maybe get an exponent and we'll try and get some quadratic function out of that and make this really hard for people to understand. So we'll introduce the universal soil loss equation today, and then later on we will talk about the interrelationships and why they came up with the revised soil loss equation. This is not going to be on the test next Thursday. This is a whole new module and chapter, okay? What we start with is we start with a t-value. And so this is our threshold. This is what we say, you know what, if we lose more than this amount of soil, we're in some trouble. We cannot sustain the productivity if we lose 5 megagrams per hectare or 5 tons per acre. They're about the same thing. I'm just so scientific that like tons per acre, and then I have to convert it back over to megagrams per hectare when I write my article, and I go talk to Michaela and her group and they don't know what a megagram per hectare is, and then I have to convert everything back over to tons per acre. It can be a mess. But just to understand that this, when you see this is megagrams per hectare. So we can lose about 5 to 11 tons per year, per acre per year. And I guess 9 millimeters is about 1 centimeter of soil, so about a ½ inch. Maybe about a third of an inch. 25 millimeters is 1 inch-ish. That's a calculated thing. So I'm telling you, someone's doing that. They're like, no, it's not. Let's just say we're losing somewhere between 1/4 and a ½ inch of soil every year. And there's nothing we can do about that because it rains, right? We need the water. All right. So the components of the universal soil loss equation, A is going to be the value that we are solving for, and we will compare that against our t-value. Next will be our rainfall erosivity. So rainfall and our soil factors, our soil erodibility and our lengths, our slope length and steepness, so how long and at what slope. These two things we don't really have any control over at all. Like, we can't fix the soil type, and we can't change the rainfall. So these are going to be constant numbers based on some table. Like, you'll go find these in a table based on your specific area. And I found a table and it's got the R values for every county in Tennessee. So when we do our exercise in that, that's the table that we're going to use. And it varies across the country, and you'll see that in just a moment. But the things that we can change are the cover and management and the erosion control practices that we use. So when I think cover and management, I'm thinking cover crop and conservation tillage. And then the erosion control practices are kind of the way that we plant our crops. And we can plant them in such a way that it diverts the water and slows that down. And I didn't understand it at first. I never understood why you wouldn't just plant in a straight row. But sometimes if you contour it to the land, and then I was like, oh, well, I guess that makes sense. Like, I don't like cutting grass that way. I will cut the curve, and then I will cut a straight. I worked on a golf course, so I will cut the curve out first, and then I'll cut a straight line, and it'll be square the rest of the way. That's just me. But for cropping, it makes sense to just keep driving the tractor in the same way. It's more efficient. But they're also doing it because you can change the way the flow of the land and the water, and you can manipulate that a little bit to keep your soil on site. Everyone good here? We understand what we got going on? All right, so there's going to be these maps. That have these isotherms, and iso meaning similar, and so these lines in this rainfall is typically about the same throughout this portion of the United States. Get down here, rainfall is really high. And so the larger the raindrop, the faster it comes down. So that's that 18.5 miles. And now they've measured the size of the raindrop, the density of it, the terminal velocity, and if anybody remembers that equation from calculus or physics or any of those, it's like exactly. She kind of gave me the look like, oh, please don't go into that. And I'm not going to. Someone else has already calculated that. I'll take your word that it's 18.5 miles an hour. So if we follow this isotherm right here in red, you probably can't see it on yours. I will try to make sure that I get a better map of this whenever we go to do our actual homeworks and practices. It took me a long time to get in here because I got all the counties and it's tight in here. So the red line would be 275, the yellow being 250, and then if we get this orange, it's 200. But down here, where I'm from, like I am from right there, that's me. Home sweet home. So we get, that rainfall erosivity is 650. Anybody know why we have so much? Why was such a high number down here? I know Miss Kitty does. What weather phenomena occurs in the Gulf of Mexico very much during August? Hurricanes. You get a lot of hurricanes that come through. You get all this moisture coming up out of the Gulf, and then it just picks it up and dumps it right back onto. So based on your weather pattern, Colorado, it might be completely different. Colorado, their isotherm may be like 12. They don't have a lot of rainfall that's causing a lot of erosion. So it's going to vary across the state. And then, again, because we can't just let it be the average, it'll vary across the times of year too. Because right now, we're not getting a lot of rainfall, but come planting season, we get a lot of rainfall. In the summer, when we needed a tassel, not so much. and then it'll rain again when we need to get in the field and get our crop out. So it rains at planting and harvest and not in between. So just think that it's going to change a little bit throughout the year. So our soil erodibility, this is going to be influenced by the infiltration and the structural stability, like for instance, right here we have infiltration and structural stability. And so we want to use no-till because we're not disrupting that soil structure. We're at least leaving it alone, letting Mother Nature and letting gravity do its own thing. Now, we may try and manipulate the soil structure 10 years ago, knowing that in 10 years we can plow it just a little bit, or maybe we can plow the stew out of it, maybe we can really break it up if we get it just right, and develop a new structure, a new soil structure, a new infiltration rate. I know at Auburn, I know in Oklahoma, maybe in a couple of other universities, they're doing long-term no-till studies to figure out how long it takes before we start to see some benefit to this infiltration, where we get some consistency in our pore space. But it takes time. So like, we're not going to go apply these practices and next year see the benefits. So that's going to be one thing that you might have to inform your boss about. Like, yeah, we're going to do this, but we probably won't see any benefit for a couple of years. It takes a minute for that ecosystem to kind of come into equilibrium and balance and start to move on. We can talk about conservation, tillage, and regenerative agriculture and all that stuff, but you're not going to see the benefits of it next year. It's going to take a couple of years before you finally start to develop why that's possible. And so here we are back to our soil properties. We heard structure, we've got texture, sand, silt, clay, organic matter, and bulk density. So all of those things that we talked about last month are now becoming applicable here this month. I guess each module will be about a month long. So now we're into, this is why we talked about those things in the beginning of the semester. They influence our soil erodibility. So the higher the K value, the higher the erosivity. The lower the K value, the lower the erosivity. They kept this one pretty simple. Expanding clays. Not the ones, the shrink swell clays, not the ones we want to build the house of the roadbed on. Blocky and platy structure. Remember I talked about platy, that the water has to travel all the way through here and then all the way back around and find the pore space in its channel. That influences the infiltration rate. Organic matter is going to hold on to some of our water. These non-expansive clays are the ones that are compacted. And so the water can't get in there and get trapped. And it doesn't shift, it doesn't move very well. That's the red clay you see out where they're building these houses and large construction sites. And granular structure. The granular structure because it allows water to move through the soil. If you can imagine taking sand and putting it in a jar, there's a lot of, it doesn't necessarily stack perfectly right on top of each other. It's irregular. So there's opportunities for water to move into it. But if you were to take a whole bunch of clay and cram it into that, like making bricks, the water doesn't penetrate as well. And so, for a Dixon, we would expect that to be what type of soil? Sand, silt, or clay? We'll just make it simple. Would you expect this to be a sandy soil? You would? Okay. What about emery? No? We expect that to be a clay soil. Right. During the process of formulating finding the values, we will go in and we would determine what the slope is, how long it is, and there's a value associated with that. So that's where they had those on. They developed that also on these 22, on these slopes. Not a big deal. Just that when they found out this was a big problem, they said we need to start doing research on this. So they set up these plots, 22 meters long, 9% slopes. They determined all of these values. You'll just go to a table and find these. You could probably even Google what is the LS value for a 4% slope that is 15 feet long. So like, it's just going to looking up a number. Finally, the things that we can control. These are the things that we do have the ability to implement into our system and potentially change our soil walls. So we can plant cover crops, or we can do tillage and no-till. We can leave our residues. And so we see that as this is Grandpa's farming practice. We till it every year. We get all those crop residues, we get all those residues turned under. And so we can see that as we leave some residues, we start to decrease the value. And when we decrease the value, we're decreasing the soil loss. You'll see that in a moment. Finally, when we leave it alone and leave all the residues out there, now we're starting to make an impact on our soil loss because the water can't get to it. If there's a layer of crop residues over the soil, it's not going anywhere. It's covered. It's protected. Obviously, undisturbed forest and dense grasses are going to be best. We can have some small grains. Cover crops is something that we use. Like later on in this module, starting to move towards the end of the semester, we'll start to develop a cover crop management plan where you get to pick out these certain species or mixes, and they'll each have a different impact on the soil loss in your field. And they'll also add some things back. We can put mulches over it just to kind of slow some of those things down. Not that you would want to keep those there for too long, they will degrade, but it's a start. It's at least to get something over the ground to stop that rainfall from hitting the soil. 18 miles an hour, hitting the bare soil, detachment, transportation, deposition. If you have mulch there, 18.5 miles an hour hits the mulch and stops. Never touches the soil. That's going to improve our infiltration. To be considered no-till or conservation tillage, we need to have at least more than 30% crop residues left. And I'm not going to steal John's thunder. Peyton, were you doing conservation tillage? I'm not going to steal your thunder. I'll let you introduce some of this stuff and give you all the pictures. But Mr. Rogers is going to talk to you about conservation tillage and the difference between conventional. I'm sure he'll bring that up. For those who don't know, our traditional moldboard plow just completely rips this soil up and sets it back down. Look, you can start to see where we have this clay soil. There's nothing going to grow in that. And guess what happens when it dries out? You've got a brick in your field now. Grandpa's still going to do it though, because he's been doing it that way forever. That's the way his grandfather did it. And If it ain't broke, don't fix it, right? Until you show them that it's broke. Then don't want to place them. What we can do is we can use a chisel plow that just kind of tilts some of that under. We get a little increase in soil structure, some pore space that's going to open up. This is one of those practices where you can manipulate some of it to increase or have better than what you had before. But we're not doing this and starting all over from scratch. We're going to incorporate some of that residue and we'll get some mineralization because our microbes are going to need the nitrogen that is in some of those plants. But man, we really want to keep it flat the same way that it was with some cover over so the rain doesn't hit it. Heaven. No-till field corn, you can see that we have this stubble left in there, and that stubble is going to slow down some of the water movement. It's just like putting a riprap. Anybody know the riprap with the rocks on the side of the road to slow that water down before it tears up that whole side? It's just on a smaller scale here in this field. For our erosion control practices, we have two types. There's like a cropping, and then there is a terracing. I think once we get on later on into our conservation practices and how we can go about this, we'll get those more in depth. But just to know that we either have a contour cropping strategy or a strip cropping strategy. So contours, strip cropping is planting corn, planting soybean, planting grass, planting wheat. That's going to change the dynamics of the water flow. Very simple. We'll look at the contour cropping. They're actually doing some stuff they probably learned in school, surveying class with Dr. Morris. What the slope is and how they need to contour that. Strip cropping, corn, grass, soybean, oats. We have bench terraces and broad-based terraces, and they're just going to slow the flow of the runoff and just kind of let that water trickle over the edge and then move on to the next one and slow it down slowly but surely, like a step down. Terrace. Coming from the Mississippi Delta, this doesn't look too efficient. However, if they didn't have that there, they wouldn't have any crops. So for me, I kind of have to go, you know what? Okay, that's cool. At least y'all are growing something. You got something going there. When you're stopping the water, the soil erosion. So that's what they need to do. Again, we have cropping and terracing and these sub-factors. If we don't have anything on our ground, that number is 1. But if we add some sort of strip cropping or contour cropping, we start to decrease that value. When we decrease the value, we're decreasing the soil loss. All right, this is where we get to do something now, finally. So we're going to calculate the annual soil loss, Knoxville on an Emory soil with our 6% slopes. Then we have our cropping system. We're going to go through each one of these step by step so you know where we're getting the numbers, what we're doing with it. So the first thing we're going to do is find our R factor. We're going to go to our rainfall isotherm map, and we're going to try and decipher where that line is. So our R factor is 200. Trust that line. I'm drawing with my mouse. Okay, there's just to get some practice about where these numbers go, and where do we get them, how do we get them. I searched night and day trying to find a better, cleaner, crisper image, but I just cannot find it. What was our soil type from the problem? It was an emery. So our K factor is going to be 0.28. Oh. Okay. Next, we'll find our slope. We had 6% slopes. (150 feet long), so our value is 107. What was our crop management situation? Conventional spring plowing, conventional till, spring plow. I'm sorry, CT is conventional till. And I hope you find something that says different what the acronym is for conservation tillage, because I hate writing CT because it just tells me that it's conventional till. Also conservation tillage? I don't know if it's CONT. I don't know. So we had spring till with the residues left, right? Yes. Okay, so our cropping factor is 0.37. For the video, spring till or spring conservation tillage with residues left, 0.37. And what about our erosion control practices? None. None. Okay, so this is we're about to demonstrate the influence of changing your erosion control practices on soil loss. So we had one. I found my R based upon my location and my isotherm. I found K, my length and slope, my crop management, and then my erosion control practices. You remember this from soils? Okay. It's okay. It's in your brain now, though. You'll know how to do it. I mean, there's only so much we can do with soil, right? So we're losing 22 tons per acre in this situation. Remember, we can really only lose about 5 to 11 and still be productive. We've got double our soil loss. We need to do something. We need to call in our NRCS soil specialist and see what they think that I can do on my land. They'll maybe even pay me some money, won't they? Because they don't want to lose 22 tons a year either. Because that's going somewhere in a watershed and screwing a bunch of stuff up. So it's cheaper to pay you. It's cheaper to pay you to implement these practices. We'll buy you the cover crop. We'll send a person out to do all the slope and leveling, and we'll even bring out the planter. We'll plant the cover crop for you, and we'll even give you some extra money on top of that. Just, just for listening to what we tell you. Because maybe we don't want to spend $45 billion cleaning up your mess because you used a moldboard plow and you don't have any cover crops over here. Everyone understanding this? Super straightforward. Everyone get the answer or close to it. It's not exactly perfect, but it should be because there's no round off error here. All right. So the hard to change factor is where we are, the soil type, and the length of the slope and the steepness. You can't change that. But what we can change is now we're going to do this with, we're going to change from conservation till, for conventional till to no-till with about 4,000 pounds of our residue left, and we'll go all the way back to our cropping. One more. All the way back to our cover and management slide and find the value that was in that table. This is on page 7. So these are going to remain the same from the previous problem, because the only things we can really change out of that are our cover management and our cropping practices. So our new cropping right here, no-till, 3,000 to 4,000. So take this. Now this goes down to 0.11. Right here. And then what was our other, what else did we change for that last one? Contour cropping on 6% slopes. Contour cropping, 6% slopes. So just by implementing, just by not tilling, not driving our tractor across the field and saving that fuel and time and labor, and by adding in some contour cropping, we've almost 7 times the reduction in soil loss, and now we're within the range where we can still be productive. Like we're less than 5 tons of soil per acre. So like, just by implementing these little things on your farm or in your land management system, you've now decreased the amount of soil loss. And guess what? That's a return on investment for NRCS. That's a return on investment for you or your farm manager or your farm owner. They got paid. They didn't have to drive their tractor across the field. They didn't have to have someone driving the tractor. They didn't have to worry about washing all their soil wash away. That's a win-win. But for some reason, people just will not do this. I don't know. I'll leave this for Peyton to kind of go over the different types of conservation tillage. This is a hydro seeder that's mulching the side of this road, or maybe even that this looks like the bowl that had that real erosion, right? So even just putting some mulch over this is going to slow down that water movement. I actually worked on, in my undergrad, I worked on a project with a PhD student who was looking at these things. Mississippi Department of Transportation was looking at different types of like straw mulch. Is it worth it having a bunch of people on the side of the road putting out this straw, or actually got to play with one of these and actually shoot from the top of the cannon with this hydro seeder mulch thing and whatever his results were, but it was better than bare ground is kind of the main thing that we need to know about that. We'll also try and implement some more of this like riprap, some retention walls, just to kind of slow the flow of that water over whatever structure that is. So get into water quality and a little bit more like water management, watershed management, anyone? You know. But y'all have seen this on the side of the roads. Anyone from Alabama? They got them in Alabama bad. Next, I guess we would be moving into wind erosion. I think we're going to hold up here. We may have to do some more work on that soil loss equation, on the universal soil loss equation. So that's what I got for today. I'm going to try and get quiz 2 up today, because I know some people need to take that before they leave out. See y'all next week.